Welcome back, guys. So this will be the last video of the contents of this chapter, and in this video we'll talk about two things. That first is about energy density. This is a direct concept which comes from the previous video, which is energy stored in a capacitor. So we'll see what is energy density, and the second part of the video, I have written a tag over here, is about the Van de Graaff generator, which is a method to store high amount of charges, which is helpful for accelerating particles. It's a practical application of one of the properties of electrostatics of conductors. So we'll see these two topics today, and for now let's start with what is energy density. Okay, so when we said that there was energy stored in a capacitor, and we found out the magnitude of that energy in a capacitor to be three different quantities, that was half Q squared by C, and then we had half CV squared, and also we had half Q times V. These three quantities we had. So when we say that this much of energy is stored in a capacitor, what does it actually mean? So that energy we can also say is the energy possessed by that electric field in between the capacitors. Like if this is the capacitor we are considering, and these are positively charged, the left side is positively charged plate and the right side is negatively charged, you know there is the electric field in between, which is in this direction, positive to negative. So this electric field carries some energy. So we are assigning the magnitude of energy of the capacitor to be as if it was brought forward because of the presence of electric field. We call this energy to be the energy of the electric field. So now, how do you bring, so you see the formulas are all in pure terms of the conductor's properties, capacitors. Capacitance, charge, voltage. But we do not have anything that relates to electric field over here. So how do we bring in an electric field term inside this energy equation? So let's see that. Like any one of these formula, it doesn't matter which one we chose because each one of them can have the same proceedings. Like for example, we are going to substitute the charge Q in terms of sigma by sigma into the area, and then we are going to substitute the capacitance of the conductor with the formula we just derived, and the same thing can be done over here for Q, and potential can be substituted. So let's see this formula and this formula, because Q, C, V and these three are the total terms we have, and others all are just going to be repetition. So let's start with half Q squared by C. If this is the formula for energy that's given, how do we bring in an electric field term into this? So let's convert this completely. So how do we convert Q in terms of something that might be helpful for introducing electric field? We know that electric field is not related to directly Q in any sense, but we know there is a formula for electric field due to a plate being sigma divided by epsilon naught, which is the electric field in this region. So we are trying to bring in sigma somehow. And which is the method to do that? We have Q, and we know Q is equal to sigma times the area, because sigma equals Q divided by area. So we are going to make use of this formula and this formula in this substitution. So let's substitute for Q. So let's substitute Q as sigma times A squared, where A is the area of the plate and D is the distance of separation as usual. So we substituted for Q. Now how do we substitute for C? So capacitance is epsilon naught A divided by D, and we just did the derivation for that. So epsilon naught A divided by D goes to the numerator. So now let's cancel out the common terms. So you have sigma square A square D divided by epsilon naught times A. I'm going to cut off one A and the squared. I'm just going to manipulate this equation so that we can bring it in terms of this. So here, for example, I'm going to square. So you get E squared equals sigma squared by epsilon naught squared. I just squared the equation. So why I did that is because we have a sigma square. We have one epsilon. So let's multiply and divide by another epsilon naught. So you have 1 by 2 sigma square as it is divided by epsilon naught squared. Because I'm going to multiply, I'll write it over here, into epsilon naught divided by epsilon naught. It makes no difference to multiply and divide, but the reason we are doing that is to bring an epsilon naught squared. So you have epsilon naught squared times epsilon times AD. So this is the expression we have for now. So I'll erase this off and I'll start from the beginning. So it would get confusing if there is one electric field E over here and an energy E over here. So I'm going to represent energy by capital U. The only reason we are using a different notation is because we are going to have an E, which is for electric field in here. So sigma squared divided by epsilon naught squared would be E squared. So it would become half epsilon naught E squared AD. And A times D, if you know, the volume of any given regular object is the base area times the distance times the height. So if you have a sheet over here which has an area A and you multiply it by the distance D, you are going to get the volume of this rectangular slab, because in reality the sheet is not just a line, it's a sheet, so it's going to look like this. Whenever we draw a diagram like this for a capacitor, when we draw the diagram like this, we are looking at it from the side. So area is not a line, area is a two-dimensional surface. So this is the area. This is how the plates actually are, right? So if it was in this manner, this entire surface is area and this distance is D. So if you connect these lines, A times D give what is the volume of this rectangular slab. So this is how the capacitor looks in reality. It's two parallel plates kept next to each other. So A times D is the volume. So I'm just going to substitute that as volume. So half epsilon naught E square into V. This is the total energy stored in a capacitor, which is basically same as the formula we started with, except now it is directly in terms of electric field, as everything else over here are constants. 1 by 2 is a constant, epsilon naught is a constant, and the volume, not voltage, this is volume. So if you want, I'll just write it as volume itself, times volume. And the volume is also a constant because area and the distance is fixed. So directly proportional to E squared. Okay, so now we have energy. Now is where we have to talk about energy density. So density, you know, it's mass by volume. Density is always per unit volume of any substance you're looking for. If you're talking about linear charge density, it was the entire stuff divided by the total area. Sorry, the total length. Surface charge divided by total area, and volumetric charge by the total volume. So when we talk about energy density, it is the total amount of energy stored per unit volume. So that means U divided by volume, which is represented by per unit volume. So we are dividing this by volume, which is represented by a small u, equals half epsilon naught E squared. We have just divided both sides of this equation by volume so that it cancels off. So this is the energy density of the electric field present between the capacitor's plates, half epsilon naught E squared. If you proceed with any of the three energy formulas we had, you are going to arrive at this final result. Except that we substituted for Q and C. So if it was directly V, as in the case of half QV, you're supposed to substitute V as E times D. We'll know the equation V is equal to ER. Potential equals electric field times the distance. So if you substitute this directly, you have an electric field in the formula. So that's how you proceed with any of the given equation. I'll write down the definition of energy density. If you want, you can note it down. This is the final expression. So this is energy density, and its magnitude is equal to half epsilon naught E squared. Energy density is this, and if you want to talk about the energy, it's just times A times D, which is volume. So this is about energy density, and now let's proceed to the next part of the topic, which is Van de Graaff's generator. Okay, so now we are talking about Van de Graaff generator. So the main underlying principle of this appliance is that what we learned in the electrostatics of conductors, which is potential at surface equals the potential at any point inside inside which is equal to a constant value. So we saw this in the electrostatics of conductors, and we also know that electric field is zero inside. So using this, let's see how we can make use of this generator. Also, the Van de Graaff generator, what it mainly serves is that it can store up to a few million volts of charge, which can be used to accelerate charged particles like electrons, protons to high amounts of velocities, and which can be used for experimental purposes like particle accelerators. So let's see how does it work. So let's consider hollow sphere, metallic conductor with charge capital Q, which means that we already saw that charges always lie on the surface. So that charge capital Q is going to distribute equally on the surface area outside. So charge Q plus 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 plus. Okay, so this is the first apparatus we have. Charge Q distributed. Now what we are going to do is that we are not talking about the means over here, as in we are not saying how it is done, but we are going to be talking about it is done, and we'll see what are its consequences. Because the way in which it can be achieved is possible by engineering, and it can be done in any way. But here we are just talking about the principles of how it is working. So we are going to introduce a small metallic ball in the center with a much smaller radius. Let's call the radius of this bigger sphere to be capital R, and let's say we are bringing in another small ball which is of radius small r and has a charge small q. So this is capital Q and capital R is the radius. This is small q and small r is the radius. We are considering all to be positive charged, and yes, so this is now the apparatus. Let me say a small sphere of radius r is introduced at the center. So far as now we are just constructing. So we have this system now. So if you notice, let's find out what are the potentials at given points. Let's take some points. Let's say this point is point A. This point on the smaller surface is point B. Okay, so what is potential at A? Potential at A is going to be, first of all, let's avoid the sphere, and if the sphere was not there, what would the potential at A be? It would be 1 by 4 pi epsilon naught k q by r, capital Q divided by r, where r is the radius of the bigger sphere, because first we are considering without this, by r. This was if it was alone, but now we have a smaller sphere in between, so it's going to experience a potential due to this. Since this point A is outside this, now we can consider as if this was a point charge capital Q and this is the point we are having as A. It's similar to consider it as this situation, as if this was a point charge. So what's going to be the potential of the smaller one? 1 by 4 pi epsilon naught small q divided by, it is still capital R. It is not small r, but it is capital R, because the distance where the point is from the center is capital R. So this is the potential at any point A on the outer surface, outer sphere. Now let's calculate the potential at the point B. Again, the same way, individual potentials are being added up, but let's find together. So let's first say this surface was not there. There's no surface, there's no inner ball over here, but the point B is still over here. So what would be the potential? The potential is going to be as if any point inside is going to have the equal potential on the surface. This was the electrostatic property we learned. Potential inside a sphere, anywhere at this point is a constant value and it is equal to the potential at the surface. So potential at B, if this ball was not there, would be potential at A. So that's going to have this same value, 1 by 4 pi epsilon naught capital Q divided by capital R. This is where the principle directly applies. And now the potential at B is also present because of the presence of the smaller sphere. So what's going to be potential at B? It's going to be 1 by 4 pi epsilon naught due to smaller charge Q by the radius R as it is. So now the purpose of finding these potentials is that we are going to find the difference of them to find out whether this or the bigger sphere is at a higher potential. So you would obviously think, since this has a higher charge Q, the potential over here is supposed to be more than the smaller charge. If you have a small statically charged ball and if you have a larger ball, you would say that this is at a higher potential, but it's not always true. As if this case, this has the higher potential, and we'll see how. So I'll erase off this construction part and let's do the subtraction. So I'm going to do V of B minus V of A. V of B minus V of A equals subtraction of these two. These two terms are the same. They cancel off. 1 by 4 pi epsilon naught capital Q by R minus 1 by 4 pi epsilon naught capital Q by R cancels off. And we have, I'm taking 1 by 4 pi epsilon naught Q constant, and we have 1 by small r minus 1 by capital R. This is the potential difference, VB minus VA. If this is a positive quantity, which means potential at B is a higher quantity. It has higher potential at point B than at point A. But if this is a negative quantity, which implies that A is at a higher potential. So let's see if it's positive or negative. You can note this down, and again I'll just go quickly about how we found these points. Potential at A is going to be the individual effects of only the bigger one, also due to the presence of the smaller one. So if the smaller one was not there, at A it's going to be capital Q by capital R, capital radius. But the smaller one also gives an additional potential, which is going to be 1 by 4 pi epsilon naught charge present on the smaller one divided by the capital R, because it is still outside. That's for A. And now for B, we saw in electrostatics of conductors that potential inside equals to potential on the surface. So if this was not there but point B was still there, there would be a potential this would experience because of this sphere, and that is capital Q by capital R. But also due to the smaller sphere, point B experiences another one, which is small q by small r. So I erase this off. And now we'll check if this is a positive quantity or not. Let's always consider the magnitude of Q. In this case, it's obvious we have taken positive, but even if it was negative, let's only consider positive value. So Q by 4 pi epsilon naught is going to be positive no matter what. They are constants. Now, 1 by small r minus 1 by capital R is what is going to judge whether this quantity is positive or not. We know that small r has a greater magnitude than capital R. So if you divide 1 by 2 minus 1 by 8, that's the condition over here, because R is smaller than capital R. 1 by 2 is 0.5 and minus 1 by 8 is less than 0.5, which is about 0.045. Which is a positive quantity. That means this 1 by small r is a greater quantity than 1 by r. So that means the potential difference is positive. Potential difference is greater than 0, which implies potential at point B is greater than potential at point A. That means the inner sphere is at a higher potential than the outer sphere. So now, since we have proved this, if you bring in a charge, if you bring in a conductor or a wire and you connect them in this way, charges will start to flow from here to there. It's just opposite of what we thought. Since even though the charge capital Q is greater than small q, the charges are still being forced to go outside. That means if you somehow had a mechanism to keep on bringing charges over here, positive, 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 those charges are going to get pushed outside in spite of this having more charge. So more and more charges are going to accumulate on the outside. This is only due to the difference in the potential. So more the charges accumulate outside, more is the electric field. More is the electric field, more is the potential developed, and this is what is used in the practical application to accelerate charges. So the main underlying principle is that when the potential at point B is greater, no matter even if the charge is greater outside, it's going to still push the charges towards the outer sphere. So this is it for today's video, and the chapter is over now. In the next video, we'll do some questions, and if you have any doubts, you can send it to my email. So thank you and see you in the next video.